Okay, so here I'm going to work assignment 8. So this is the momentum problem, and we're going to do this. I'm going to do this two ways. The first way I'm going to do it is the way that I did it on the key, and then where my free body diagram had it included the nozzle, and it did not. It was not just the water. And then I'll do it again where I just do just the water. And a lot of you guys try to do it that way because that was the way I did it in class. So let's zoom in. I think pretty much everything, it's a little blurry on here. Luckily you have a copy of this, is hopefully a little bit better. Pretty much everything is already on this diagram. But we're going to go ahead and do a free body diagram because the only thing that really needs to be added on is this, not this velocity, sorry, the weight of the nozzle. So I'm going to do a free body diagram. And one thing a lot of you guys did not do is you didn't tell me what it was a free body diagram of. So I'm going to do the nozzle with the water. Okay. So basically I'm going to cut my diagram here and here. Okay. So here we go. And it's got a little bend to it. And I'm going to leave it kind of open on that end. Like sometimes I'll draw it like that. So this means the water's exiting to the atmosphere. So we've got a jet leaving this way, and that's we'll call it V2 equals 130 feet per second. We've got V1 right here. Okay, and we don't know what that is. And then we've got other forces. So I cut it down here, as you can see. Okay, so what was left behind was there's a pressure right here. Okay, so that force, that's P1A1. It gets a little bit sloppy when you don't have different colors. There could be a P1A1 up here, or P2A2, but that's atmospheric, so we're going to make that 0. Okay, and then we've got, so we don't have to worry about like viscosity or the force of the bend on the water or the water on the bend, because all of that is interior because I'm doing this free body diagram of the nozzle with the water. However, there is still the body force of the weight of the water, and there is a weight of the nozzle, okay, because I'm kind of drawing this whole thing. Okay, so then the other forces on this are, I'm going to have to support this. Okay, so I'm going to assume that I'm going to push upwards to support it. And that may not be the case. So I'm going to call it F anchor in the Z direction. Okay, and there's also going to be, F anchor in the X direction. Okay, so I guess the only other information that you might want on this is you might want theta equals, I think it's 30 degrees in this case. Okay, so now when we solve this, okay, and now that everything is on here, well, I guess I didn't put that the weight of the nozzle is, this weight of the nozzle is 100 pounds. And, we'll have to get the weight of the water. So I'm going to do the momentum equation. So momentum equation in X. So momentum, not in X, in Z. In Z. Okay, I'm assuming this is my coordinate system, X, Z. Okay. So momentum equation is sum of the forces, in general. Let me do it right here. So the momentum equation in general is sum of the forces equals, it depends on how people do it. A lot of people do it different ways. Let me erase that. Where's my eraser? I'm trying to find consistency here, and because it's confusing y'all. Plus in sum of m dot v, okay, in equals the sum out m dot v. Okay, so that's momentum in general. Okay, and now if we're going to make it in the x direction, what we can do is we can get rid of this, arrow right there on top, and we can say the sum of the forces in the x direction plus the sum of m dot Vx, okay, that's in, equals the sum of m dot Vx out. Okay, so the arrows got replaced with the letter x. Okay. So I'm going to split this out here. Oh, not x. Sorry, we're in the z direction. This is really... Okay, let's get rid of those. Make them z's. Okay, z, z, z. Okay, so we're going to split out the sum of forces in the z direction. So what do we have? Let's see. I'm going to kind of start at the bottom. We've got P1A1. Okay, I've got minus weight of the water, minus the weight of the nozzle. Okay, W nos. I've got plus F anchor Z. Okay. And then P2A2 is 0, so we don't have to account for that, although if we did, it would have a sign on it because it's on an angle. And those are all our forces in the z direction. Okay, now do we have any momentum? So now we're going to split this out. Do we have any in momentum terms in the z direction? So it turns out we do. We've got this V1 here. So we're going to say plus, so m dot is rho q, okay, and then vz. So that's going to be v1 because it's in the straight up direction. Now, note that if v1 were down, like if this thing were upside down, if v1 were somehow flowing into the control volume in a downward direction, that would be a negative v1 right there. Okay, so then we'll say equals. Do we have any outs? And it turns out we do. We've got this one is going out. So I'm going to make that m dot rho q, okay, times vz, or the velocity out in the z direction. So that's going to be v2 sine of, we'll just call it theta now. So this is our equation. I'm going to go ahead and check it and make sure that I didn't do something wrong, so I don't have to send you guys all a retraction. No, so this is exactly what I got on my sheet. And so as an aside, I'm going to go over here and I'm going to notice that I need some of these values. Okay, so I'm going to start with the easier ones. Maybe, well, I don't know. Let's just go in order. Okay, so I need P1. Okay, so I need this thing right here. Okay, so to get P1, I'm going to do Bernoulli. Okay, and I'm going to go from, if I go back to my original diagram, I'm going to go from this will be 0.1 and this will be 0.2. Okay, so I'm going to go back over here and I'm going to try to leave where we can see that. So that's P1 over gamma plus Z1 plus V1 squared on 2G equals P2 on gamma plus Z2 plus V2 squared on 2G. Okay, so already I'm noticing a problem. I wanted to go in order because I wanted P1, but the problem is I don't have V1. So I'm going to go ahead and do that. Okay, so now these asides are kind of getting out of order. But it's okay. So I need V1. Okay, so let's go ahead and do continuity. Okay, so we're going to go V1A1 equals V2A2. Okay, in equals out. Okay, technically there's a row here, but it's incompressible, so those rows go away. Okay, this is what, water? Yeah, water. Okay, it's water. Okay, so so this is all going to go away. Okay, so V1 is what we're looking for. A1 is, what is A1? Oh, it's given. Okay, so it's 1 square foot equals V2, which is 130 feet per second, and A2, which is a half a foot, square foot. Okay, so V1 then is 65 feet per second. Okay, and while we're here, I know that I'm going to need Q as well. So Q equals V1A1, and And if A1 is 1 feet per second, or 1 square foot, then Q equals 65 CFS. Okay, I'm not going to plug that in for you. I think you can do that. Okay, so that allows me now to do Bernoulli. So I'm going to go back in over here to my Bernoulli equation. And we're looking for P1. So P1 on gamma plus Z1. If we go over here, I'll make, this is the datum. Okay. So that means Z1 is 0 feet. Okay, V1 is 65 feet per second squared on 2 times 32.2 feet per second squared. Okay, so that's going to be roughly of the order of 65 equals P2. Now P2 is exiting into the atmosphere. So this is going to go away because it's atmospheric. Just as this went away because it's a datum. Okay, Z2, 0 feet plus Z2 is going to be 2 feet. Okay, and then V squared on 2G. Well, V squared is 130 feet per second squared on 2 times 32.2 feet per second squared. Okay, so if we work that all the way out, we'll get that P1. Oh, I didn't put in the 64 or 62.4, but P1 equals 12,406 PSF. I think it's interesting to note that this value right here, this 2 feet, is very small compared to this term, which ends up being 262-ish feet, or this one, which ends up being 65.6 feet. Okay, and so when you work with these sorts of problems a lot, sometimes with a 2-foot bend, with a bend that has 2 feet, you might just ignore it. Okay, and if you were to ignore it in this case, it's not really going to create much of a problem. Almost all of the head in this problem is wrapped up in this velocity head and also in this pressure term over here. So anyway, so we have that value. Okay, so we've got P1. A1 is given. The weight of the water, okay, that's another aside. Okay, weight of the water equals gamma times the volume. Okay, so the weight of the water equals gamma, which is 62.4 PCF. And the volume of water, I think was given as 1.8, I believe. Yeah, 1.8 feet cubed. Okay, so the weight of water is 112.32 pounds. Okay, so we're going to zoom in here. So we've got this. Check. The weight of the nozzle is given. This is what we're looking for. We know the rho. We solve for the Q. We've got V1, rho, Q, V2, sine theta. Okay, we know all this. So we can start plugging and chugging. And in fact, I'm going to pause this and just write it all down because you don't need to watch me do this. Okay, so if I just kind of zap forward and I've kind of entered in everything, remembering to account for this sine at this angle, we get this longer equation, and noting that the momentum terms in z, they cancel each other out. Now this is a totally coincidental, and it has to do with the fact that the sine of 30 degrees is a half, and it just so happened that the velocity in the at the opening is twice as big as the velocity up here. Okay, so that 2 and that 1/2 kind of cancel. It's totally coincidental. It won't normally work out that way. So then our F anchor Z is ends up being negative 12,194 pounds, and as I prefer to do it with 3 significant digits, go negative 12.2 kips. Okay, I think sometimes they do a little like lowercase k for that. Okay. And just for fun, we don't really have to do this, but I did it on the sheet. Like obviously you weren't graded on this, but the momentum in X would look like this. Okay, sum of the forces in the X plus sum of m dot v. Oh, nope, not that. Come on, you can do it. Okay, mvx equals the sum of m dot vx. Okay, this is going to be out. Oh, sorry, that's going to be in. That's going to be out. Yeah, and this will be in. Okay, so so what we're going to do here is same procedure. I want to look at my free body diagram, which is like right there. Okay, the nice thing about in this case is there's not really that much going on in the x direction. Okay, the only force in the x direction. Okay, it looks like the only well there would be a P2A2, but there's no pressure there. So the only force in the x direction is F anchor x. Okay, there's no momentum going in anywhere in this problem, so this goes away. Okay, equals, well, this thing leaving, the V2 exiting. So it's going to be m dot, which is rho q, and the velocity in the x direction here, which is going to be V2 cosine of theta. Okay, a much simpler problem, the x direction. Usually on tests, I like to ask just one direction, so that we're not spending our whole time on that. No saying what I'll do on this test, but usually a lot of times I ask for one direction, and that's kind of what I did on this, is you know, just to kind of give you that thing, that possibility. Okay, so here we go. F anchor x. Now, the nice thing about this is it's all ready to go. We've already done all this, so I already know all these values. So again, I'll just pause and put them in there. All right, so there you go. I just kind of like zapped it all in there. Let's just plug in the numbers in, and F anchor x equals 14.2 kips. Okay. So what that means is, and again, I'm going to do this real, you know, I'm just going to like F anchor in general. If somebody had asked for the, you know, the total thing, we would do the square root of F anchor x squared plus F anchor z squared. Okay, and we would get F anchor equals, I'm just going to give it in the reported version, 18.7 kips. Okay, and if we wanted the angle, we would do, it wouldn't be theta because we've already used theta. It would be alpha equals inverse tangent of F anchor z over F anchor x. Okay, so alpha would then, if we plug those numbers in, it would be, well, if you put signs in there, it's going to come out as negative 40.7 degrees. Okay, so that means that this anchoring force is going, so anchor x is in this direction, anchor z is in this direction, so it's going like that, and this angle is 40.7 degrees, and this is 18.7 kips. Okay, so that would be the resultant. Okay, and I guess that makes sense if you stare at this thing, you know, you think about it, you know, if you stare, you're like, well, you know, which way am I going to have to push on this thing? You know, what's it going to be wanting to do? So as this water comes through here, okay, I think it's easy to, it should be easy to imagine that you're going, that in the, well, they call this the y direction, I call it the z direction, but you're going to have to push downwards, okay? And that's really because of the tremendous amount of pressure that is right in this area. Okay, so you're going to have to push downwards. And then as this jet exits, okay, it's going to try to drive the you know, it's going to be like a rocket trying to push this thing to the left. So you're going to have to push to the right, okay? So it makes sense that you're going to have to push generally in that direction, okay? And that's what we found. You're going to have to push that way with, you know, 18.7 thousand pounds. Okay, pretty crazy. Okay, it's not Dooku's lightsaber. All right, obviously you can stop here. I'll work this again where I just do the water. Okay, and I'm just going to erase a bunch of this because we'll do it right on top of it. Give me a second. Okay, so I've deleted a bunch of stuff, and we're going to zoom in here. All these asides, by the way, still hold. Okay, all these asides still hold, so we don't have to do all that. So this won't take very long. Okay, so if we go up here, I'm going to do a free body diagram of the water. Okay, and so that means that we are now in. Okay, there is no P2A2, so we're gonna. I'll write that back in there. It just happens that the P2A2 happens to be 0 in this case. Okay, P2A2. Okay, so we have the exact same free body diagram of the water, except there's going to be two notable changes. Okay, one, the weight of the nozzle is not acting on the water. Okay, so this goes away. Okay, this F anchor, we don't actually anchor the water. The water is being pushed on in multiple different ways by the bend. Okay, so you'll see me oftentimes, I'll call this F bend on water Z. I'll keep Z, even though this problem actually had it in Y. And this becomes the force of the bend on water in the X. Okay, and you're like, well, what difference does it make? It doesn't make a huge difference, but I'll show you. It kind of adds a step. So if your question asks specifically for the force of the water on the bend, then this is how you would solve it. If you asked instead for the anchoring force, you probably want to just draw the whole object. I think when I solved the one in class and most of mine, I usually almost always draw the water. It's not necessary. It's just the way that I've kind of gotten a habit of doing it. I think drawing the whole nozzle is going to be a little quicker in this case. It's definitely going to be a little quicker in this case. But let's go ahead and solve this. So it's going to be the exact same problem. So the forces, momentum in the Z. Now this is on the water. So we've got force BOWZ. Okay, minus the weight of the water. Okay, plus P1A1. And I think that those are all of our forces. Okay, and then we're going to have plus, this thing is going to get split out. It's going to be just like the last time. So it's going to be rho Q V1 equals rho Q V2 sine theta. So in other words, this is the exact same as last time, except I have a different name for this force, and I got rid of that the weight of the nozzle. Okay, so if we solve this, we can plug out all the exact same numbers, and basically we'll get the exact same solution. Okay, and the only difference, of course, is the weight of the nozzle. Okay, and that's not what we're looking for, unfortunately. So, so then we'll go down here, and we'll do momentum in the X direction. And again, well, in this case, there's nothing different. Okay, because there's no weights that are, if we look at this free body diagram, it's all the same. The only difference is this forces, when I break it out, this is going to be the force bend on water in the X direction equals, it's going to be exactly the same. So give me 1 second. Okay, so, no difference at all. So the problem is we're not all the way to our solution, so we would basically have to take both of these, okay, because that's the force of the bend on the water. And now I would have to draw a free body diagram of the bend, okay, of just the nozzle or the bend or whatever you want to call it, okay. And so that free body diagram would look like this. Now, luckily, it's a simple free body diagram, right? That's the bend. And it's got, so it's going to have basically the opposite of these. Okay, well, sorry, this one up here needs to be a negative. No, wait, sorry, this one's a positive. Yeah, this one's a negative. Give me an eraser real quick. Eraser. So this needs to be equals and negative. Okay, so F bow Z equals 12,294 pounds down. Okay, so this one is going to the right. Okay, so I'm going to draw these on here. So the force bow on water Z is downwards. So the force of the water on the bend is upwards. Okay, so we've got 12,294 pounds going upwards. The force bow X, the force water on bend, force WOB is the opposite of this. So it's going to be going this way. And that's going to be 14,197 pounds. Okay. And then we've got a weight of the nozzle. Okay, so now the water is pushing on it up and to the left, and the weight is pushing down. And in order to resist that, we're going to need the force anchor in the X and the force anchor in the Z. Okay, now you can see that this is a little longer way to kind of get around to what we're doing. What's going to happen here is the weight of this nozzle is what? What is the weight of the nozzle? 100, 112, I can't remember. 100. That's 100 pounds. Okay. So what ends up happening is if we sum the forces in the Z direction, okay, they add up to 0, and the force anchor in the Z direction, you should be able to see we just got this 100 combining with that, and we're going to get the number that we had a second ago, which is ultimately it's going to be 12.2 kips, okay, and it's going to be negative, okay, it's going to have to be negative, right, and then we could do the sum of the forces in the X, and there's only one force in each direction, so F anchor in the X direction is going to be 14.2 kips. Okay, so I think the first way that I did this is probably going to be a cleaner, faster way to do it. This is another way, and you should kind of be comfortable with both, just because sometimes you want the force of the water on the bend, and sometimes you're going to want the force to anchor the bend itself. And so it just kind of depends on what you want. If you want the forces on the water, draw a free body diagram of the water. If you want the forces on the bend, draw a free body diagram of the bend or the nozzle, whatever it is. Okay, so hopefully this was helpful, and I'll talk to you later. Oh yeah, obviously you can combine these and get the answer that we got earlier. Okay, so, all right, anyway, that's it. Take it easy.